So in this session we'll go for the second set of our experiment number 3, that is nothing but a full wave rectification. Okay, so we know how is a circuit. So as been discussed in the previous session, so we have implemented simulation of precision half-wave rectifier. So in this session we'll be working on simulation of full wave rectifier. Okay, so this is the circuitry, okay, which has been designed, okay, with some design rules. So let me define the problem statement. So our intention, our aim is to design a precision full wave rectifier for which we are going to apply an input voltage of 2.5 volts peak, and we are expecting an output voltage of 8 volts. Okay, so with respect to this constraint or contingency, we are able to design the values for the various resistors onto my circuit. Okay, so let me have my circuit for a full wave rectifier, specifically precision full wave rectifier. Okay, so if you observe this waveform, if you observe the circuitry, you can simply say that this is a precision half rectifier and this is a summer circuit. So wherein one of the input is the original signal and other input is the input from your half wave rectifier. Okay, so let us build this circuit now. Okay, I've just opened up my multi-sim simulation tool. So I'll go to place command, click on component. So I'm having diode, so I'll just have a copy of it. Then I'll go to the next component, basic, click on resistor. Okay, then after having this component, so I want op amp, so I'll go to analog. I make sure it's 741 op amp. I'll have a copy of it. Okay, so I've taken an op amp, a resistor, diodes. So I do require sources now. So I'll go to sources, click on VCC, then I'll click on VEE. Then I do require ground at certain instance. Okay, then after having this, now I'm done with respect to the components. Okay, so I just need to have a signal generator or a function generator along with an oscilloscope. So it's wattmeter along with an oscilloscope. Okay, so let me have this op amp in center. Okay, so if I see to my circuit, I'm having 2 op amps. Okay, so what I will do, I'll just take a copy of this and place it so that I can adjust my other components in line with that. So this is my function generator, my input component. Okay, then I'll be having this circuitry as an inverting amplifier circuitry, making sure this gives me 1/2 of the output, and this takes care that op amp doesn't enter into saturation. Okay, so I'll just have this diode. Okay, I'll just rotate this. Okay, I'll take a copy of this. I rotate it so that it makes sure my op amp will not enter into saturation. So this is a negative voltage. Okay, so over here I need to make sure my op amp is flipped, so I'll just flip it vertical so that inverting terminal comes on top. Okay, I'll have a copy of this over here, and then I'll take my VCC, I'll place it. Okay, I'll just copy it and place it over here. Okay, then I'll have this oscilloscope to measure my output and input signals. Okay, so I'll use this resistance now to build my inverting amplifier. So second resistance on top. So if required, I'll just take it nearer. Okay, and I do require one more resistance to make sure the biasing current is same between the inverting terminal and the non-inverting terminal. So I do require this ground over here. Okay, I also require this ground for my input signal. Okay, then this is my summer circuit, so I'll just move it aside. Let me have it there itself, not a problem. Okay, just I'll reduce the distance so that circuitry will take sufficient space. Okay, so I'll build a circuit now. Okay, so if I refer this circuit, so this is nothing but my summer circuit. So I'll have a copy of this resistance and place it over here. Okay, so I do require a ground. Then, so as I said, this is an circuitry wherein it takes two inputs. So I'll be having two resistors over here. Okay, and one more resistor is a feedback resistor. Okay, so if you want, you can have a load resistance as well. You can place it over here. Okay, so now left out is only I need to interconnect these components. So starting from the input to one end of the resistor, another end of the resistor to the inverting terminal. So in other terminal of the signal generator to ground. So I have to provide this as a feedback. So I'll connect one end of the resistor to inverting input terminal, and another terminal of resistor will be connected to the output. Okay, as of now let it be like this. If required later I can adjust it. So this is one end of the diode connected over here. So I'll just move it aside and drag it over here, and I can place my diode over here and connect this diode one end of the output, another end to the feedback component. Okay, then connect this resistance to non-inverting terminal of op-amp, other resistance to ground, give the biasing voltage, a negative biasing voltage as well as a positive biasing voltage to the circuit, to this part of the circuit. And as I said you, this is a summer circuit, so let me make sure that this end is connected to the resistance, another end is connected to the ground, this is connected to your biasing voltage. Okay, so this portion is your load resistance. Okay, and this has been connected over here. Okay, and another end of the resistance is connected to the ground. Okay, now I can just have the connection over here, that one end of this resistance is connected to inverting terminal of op-amp, and even this is connected over here, so that two inputs can be procured at this terminal. So this is also connected over here at the same terminal, and this will be connected to the output of this op-amp. So as I said, one of the input will be output from half-wave rectifier, so that I can provide it over here, and another input will be from the original signal. Okay, so for a good clarity, I'll take it from top so that it gives a clear vision that I'm taking the second input from the original, sorry, it has to come from the original signal. Okay, so I need to connect it to other end of this resistance. Okay, I just adjust it to top. Okay, so this is how is my circuitry. Now I need to just fine tune this circuit. Left out is only my input output waveforms. So let me say channel A, I'll connect it to my output. Okay, and channel B, I'll connect it to my input. Okay, since my input is coming from this terminal, so I can tap it here itself. Okay, I'll just connect it properly. Okay, and I can just short these two terminals and connect one ground probe over here. Okay, so now I need to just fine tune the circuit. So this is 4.7K, 9.4K. So this is 4.7K. This is 9.4K. Then this is 3.3K. This is 3.3K. Okay, so these are silicon diodes. Then next I need to consider the values for the resistance for the circuit, which are working like a summer circuit, which are 4.7, 4.7. So this is 4.7K, and this is also 4.7K, and this resistance we're going to consider this as 2K. Okay, and this resistance is 15K. Feedback resistance is 15K. Okay, and this resistance I can keep it to somewhere around 10K, a load resistance. Okay, and I need to set the biasing voltages properly. So this is -12. Okay, so it's minus, already set as -12. This is +12. It's also +12. Okay, so once this circuitry is fine-tuned, okay, to the designed values, now I can run the simulation. So if I open up the simulation tool, one thing we just forgotten over here is that we have to set the appropriate input signal as per my design. So if I go back to my problem statement, so there I have defined what should be my input voltage. My input voltage should be 2.5 volts peak. So I'll just double click on this function generator, let the frequency be 1 kilohertz, amplitude be set equal to 2.5 volts peak. Okay, so first I'll have only my input. So this is input signal. So if I see what is the voltage, so it is 1 volts, 2 volts, 2.5 volts peak. Okay, now if I see what's the output voltage, so it's a rectifier, output voltage has to be in terms of DC. So I'll just make my input 0. I simply mean to see, I don't want to see my input over here. If I see my output signal, so it's a full wave rectifier. Okay, so I want around 8 volts of output. So this is 5 volts per division, so this is 5 volts, so these are approximately 8 volts. Okay, so if you want to see the same in terms of a grapher, you can just plot it over here and stop the simulation, run it. Okay, and you can check it by flipping the color, applying the grid. Okay, and if you want to just measure the signal, then you can just measure it by properly scaling it, you can see the output nature of this particular circuit, wherein this is an simple precision full wave rectifier. Okay, thank you.